started, normally I read the bio of the speaker and make something up. So I'm going to introduce Joel, who's over there. He actually spoke in the first months of our first year, so yay. So Joel studied with Krohn-Rhodes, receiving his PhD in 1994 for generalizing the KR theory to finite algebras. Now he's applying semigroup theory to replication and convergence in distributed systems. Joel loves performing in musicals and has been an extra for Cats on numerous occasions. Let's give it up for Joel.
You all know how to add numbers with carry, at least if you balance your own checkbook, or maybe you don't do that, maybe you use an app for that or something. Very easy, you add in the ones column, you get a number out of the ones column, you carry something over to the tens column, and so on for each of the columns. It's a very simple sequential process. It's very easy to sort of automate that in your head. The important thing to notice about this is that data only flows from right to left. It's only going in one direction. You do everything in the low order digit independently of everything else. Then you move to the second digit, the mid order digit, and it depends on the low order digit, but nothing else. And then you proceed on up to the next higher digits and so on. So this is called a sequential coordinate system. And that's in contrast to a parallel coordinate system where there is no data flow among the coordinates. You can compute in each coordinate independently of the others. And these are really familiar things. You've all used Cartesian coordinates for a lot of things. In a vector space, you have vector addition. How do you add two vectors? Well, you take the first two coordinates, the first coordinate of the first vector, the first coordinate of the second vector, add them, and then add the second coordinates of the two vectors, and so on. So it's much simpler. There's no data flow between the two coordinates. So we're going to look more at this sequential idea. Let's take our add with carry example, and instead of looking at it as a binary operation where you take two vectors or two triples and combine them somehow, we are instead going to think of this as a function that acts on triples. And this is important because you might want to make a network message out of this that packages up one of the operands, but not the other one. So the x and y are unknown, but the 2 and the 5 are known in this example. So you send a message over the network saying, add this pair with carry to the current state, whatever it is. So we need a way of representing what that function is doing. How do we express that if we're not looking at a binary operation? So a natural way to do it is in terms of a table. This is kind of a brute force approach. It's maybe not the simplest, but it has a lot of, gives us a lot of possibilities. So we have a pair, and on the right-hand side of the pair, you see there's a add 5 to x, just a very simple operation, just like we would do in one coordinate by itself. But in the other coordinate, we've got this table. And the way this table works is that when we add 5 to x, we remember what x was. And then we go look up x in the table. And if x is 0, 1, 2, 3, or 4, the right-hand side of the table tells us what operation to use on the y coordinate. If x is 5 through 9, then we use something else. We use y plus 3. So this is just another way of representing what we did with the carry bit, except instead of adding an extra bit, we're representing that as a table-driven process. We're encoding all that information into a table. And you can check that this is doing addition, that we've taken two base 10 digits and we're adding base 100 correctly. That's why 0 through 4 behave one way and 5 through 9 behave another way. But the tables could be filled with all kinds of other operations. We could just sort of randomly fill it with other addition modulo 10, y plus 3, y plus 8, whatever we want. We won't build up addition modulo 100 that way. We'll build something else that's crazy. But just think of all of those possibilities for a minute. Those functions still compose into other functions of the same form. So they're closed under composition. So if you write down an example with two of these, it's very easy to see how the composition, what the table looks like for the composite of these two functions expressed in this way. Who knows what this does? We started with two base 10 addition operations, but now we're doing something weird and crazy. We're not doing base 100. So we constructed this semigroup, and I'll tell you more precisely in a minute what that is, but we constructed these functions using these tables and this sequential flow from right to left. This is called the wreath product, and in this case, it's the wreath product of two groups of integers modulo 10. This is a huge object. It's got lots of different functions in it. You can imagine you fill in that table in arbitrary ways and you get thousands of possibilities. But what we've shown by looking at that add with carry example is that you can pick out among all of those possible operations, you can pick out just what you need to do addition modulo 100. So it's not exactly the right terminology, but I'm going to say for the purpose of this talk that we've embedded Z100, the group of integers modulo 100, in the wreath product of Z10 with itself. So just to formalize now, I'm sure most of you have heard what a semigroup is or a monoid, pretty similar concepts to each other. A semigroup is just a bunch of things that's closed under a composition operation. And the composition operation has to be associative. It doesn't matter where you put your parentheses. It only matters what sequence they're in. Not necessarily commutative. You can't change the order of things, but you can group things arbitrarily. Associativity is easy to get if you start out with functions. If you have a bunch of functions and you close them under composition, that's always associative because function composition is basically an associative operation. So let's look at some examples. We've seen some abelian groups, these cyclic groups, integers modulo 10, modulo n, whatever. And abelian groups in general are the ones that are commutative, and of course they have inverses, x minus x equals 0. Those are the two things that make a group abelian. We're writing a plus and a minus there instead of multiplication just because that's historical standard. Another important class are the semilattices. You can think of semilattices as sort of a piece of a Boolean algebra. You've got a truth and a false value, and you have the AND operation on them, binary operation. Or you have the OR operation. They're both semilattices, and they're kind of the same thing. And they're commutative, and they also have another property. They don't have inverses, but they have idempotents. You take any two of the same thing, and you operate on them, and you get the same thing. True and true is true, so on. So those are two of the very basic pieces that we're talking about. If you take arbitrary functions on a set, you get all semigroups, basically. Any semigroup can be expressed as a set of functions on a set. If you take all permutations on a set, this is where you get groups. Groups are semigroups that have an inverse. Okay, so with these basic pieces, we're almost there. We need one more basic piece before we can state the theorem. This is called the flip-flop. You can think of this as a memory location, a kind of a minimalistic memory location. It's got one bit of storage. You can write a 0 to it, you can write a 1 to it, or you can do a no operation. So there's 3 operations you can do on it. And its state transition diagram is extremely simple. And as you play around with it for a little while, you can see that whenever you multiply things, that's not quite correct there. Whenever you multiply things that are not the no-op, it's always the same as just taking the second one, x times y equals y. So it sort of forgets everything you've done before and just takes the last one. And they're idempotent too for the same reason. Okay, now we have the theorem. Kind of amazingly, oh wait, I want to go back and just say one more thing about groups. Groups are kind of the special snowflakes of the semigroup world. If you look at groups that have, if you look at semigroups that have 8 elements, there's only 5 groups, but billions of semigroups. So they're extremely unusual if in a sort of a random noise sense. So this is part of why the theorem is so surprising. It says if you start out with this one kind of quirky flip-flop that's a minimal register, and you throw in all of these special snowflake permutation groups, combine them with this table-driven construct that we saw before, you can construct any finite semigroup. That's really kind of an amazing property. Nobody expected this to be true. And furthermore, you don't have to just take whatever groups you need to construct it. You can actually choose the groups to be things that are naturally occurring inside of your semigroup. So that means that one way of reading this theorem is that semigroups decompose into their component pieces. So Krohn-Rhodes submitted their dissertation to Harvard and MIT, respectively. They submitted identical dissertations. And of course, there was a big fuss about that. They weren't going to get their degrees, they were going to get kicked out, whatever. So they talked to the deans and argued, it's worth 4 theses, we only want 2. And the argument worked. They got their degrees. So what did they go on to do after that? The biggest problem they worked on is the question of group complexity. This is not really related to like space complexity or time complexity. It's sort of going off into a different dimension and talking about algebraic complexity instead. So we have these alternating decompositions. How many groups do you actually need in them? Do you need arbitrarily many? How can you minimize them in some way? That's known as the group complexity, the smallest number of groups that you actually need. And somebody's worked out that if you take the 19 by 19 Go game, which means you take the state of the board as your state and moves, I think you restrict it so that it's just kind of moves that make sense, you know, moves that a sane player would make. That's actually complexity at most 200. And I don't know whether anyone's come up with a lower bound for that. However, if you want something a little simpler, if you think in biochemistry, there's this reaction called the Krebs cycle, or a sequence of reactions that involves ATP and ADP and sugars and so on, the basic energy reaction in the cells. The complexity of that reaction is only 2, which is actually still pretty complex if you actually write it down. So the other questions here, is complexity bounded? No, you can find semigroups that are as complex as you want them to be. Is it decidable? We don't really know for sure. It's been worked on for like 50 years and everybody thinks it is, but the proof is still not quite there. Okay, so let's, unless there's any questions with the algebra, let's go on back to distributed computing, which is why we're all here, I hope. So in distributed computing, there's this idea called a commutative or convergent replicated data type. And one example is a 2-phase set. It's a way of handling set insertions and deletions in a distributed environment. And I'll tell you why that works in a second, how you make that work. But you may have run into this in Cassandra, for example. They have something called tombstones where you can mark something as being deleted. But the idea is this, that you want to have a register that can be empty, to hold the empty set, or you can add something to it, a little smiley face, or it's going to need one other state that it can be in, an error state. So we have 2 operations. We can add smiley to the set, we can remove smiley from the set. And their state transition diagram is really quite simple. If you add and then remove, you get into that state on the right from which you can't get out. You're basically stuck there. If you remove before adding, you get into the error state, and again, you're stuck there. One thing to note is that the state on the far left and the state on the far right, they both look like they have the empty set in them, but they're actually different states because the machine remembers whether you've done anything yet. So there's the initial state and then there's the final state. The reason they have the same value in there, that's sort of the queryable value, the thing that an observer would be able to see. But they're still different states. Okay, so a couple of... Question? Oh, sorry.
No, I just said it's hysteresis.
Yeah. So you can study the composition of these operations. If you take 2 A's and compose them, that's the same as an A, and so on. And it turns out that all you can get by composing these things, is AR and AR. There's nothing else. And the multiplication table for those is also very simple. You just apply those observations, and that's about all you can do. So why do you want to do this? You have an asynchronous network. You have multiple people in the network sending messages. They arrive in different relative orders. They might get interleaved differently. And you want the result to be the same however they get interleaved. So in this case, you look at all the possible interleavings of Bob's message into Amy's sequence of messages. Those actually turn out to be the same they're all AR via the equations we had on the previous slide. So the server will end up in the same state regardless of how the messages are interleaved. And that, of course, is something you want for convergent replication because the interleaving might be different on different servers. Okay, so back to the algebra, and this is where things get really kind of interesting. We can decompose this little algebraic structure, and it's kind of revealing what it turns into. So we're going to think of the state that we're operating on as a triple of Booleans. We have a flag that says, has there been an error? A flag that says, have we done a remove operation? A flag that says, have we done an add operation? And the way the two operations work on this is add is very simple. It just flips up the a bit, the x component of that vector. The remove operation is much more complicated. In two coordinates, it's the same kind of a thing. It flips up the remove bit. But in the z coordinate, the error coordinate, it has to do something special. And this little table here is the same thing that we were looking at a minute ago with writing modulo 100 arithmetic in terms of modulo 10 arithmetic. So to see how it works, let's look at an example. There's R again. Suppose we start out with the initial state of 0, 0, 0, blank slate. How does R apply to that? Well, it doesn't do anything to the x. It flips up the y into a 1. But what does it do to, because that signifies that R has been done. But what does it do in the error coordinate? Well, in order to do that, we have to do a table lookup. We have to look up the x and the y value, 0, 0, in our little table. And we find the entry there is an operation. It says z or 1. So it's the operation which flips up 1 in that, flips up the bit in that column. So that we end up with a state that has a 1 in the z column, which means we're in an error state. So what that really means that we've done is we've decomposed this two-phase set semigroup into 3 semilattices. This is a special case of the Krohn-Rhodes decomposition. It's just a very simple one that doesn't have any groups in it. So why do we care about this? There's another thing you can prove in semigroup theory. I say theorem here, but it's actually an exercise in basic classes. It's really easy to prove. You can decompose a semigroup into semilattices if and only if there's a partial ordering on the elements of S for which multiplication is monotonic. What does monotonic mean? It just means that the product of two things is below the first thing. So as you multiply more things, you keep going down, or you stay at the same level or go down in that ordering. Well, why do we care about monotonicity? Monotonicity is necessary for confluence. Confluence, I don't want to get into the definition here, but roughly the idea is it's stronger than convergence, but you also avoid oscillation, so that as you're watching this system converge, you can take a snapshot of it at any point and rely on whatever you saw there, because things are only going to get more so or less so, whichever direction you're looking. And so monotonicity is necessary for that. Sufficient is a different question and kind of a complicated one, I think. It's not fully resolved as far as I can tell. So what this means is that if you have a confluent system, if you've built a computer that not only converges but doesn't do any oscillations while it's converging, the state always monotonically progresses towards the converged state, then that computer could actually have been built in terms of the wreath product, in terms of semilattices using the wreath product. So things that I like to think about in this picture of the world is we've got these algebraic constructions and we've got distributed systems properties. How do they match up? What about other algebraic constructs? What if we start with other pieces besides semilattices? I think there's a lot of interesting things to discover there. And another thing is, we got up to the level where we're just talking about composition of operations. We're not talking about how they act on state. We can talk about the wreath product of semilattices without talking about what those semilattices are actually transforming. So we're talking about just composition of operations and not operations as mappings on state. And it's interesting to me that moving up to that sort of functional level, we're still able to say quite a lot of things about the distributed system behavior of these structures. And so that's it. Any questions?
Questions? That was not supposed to happen.
Well, come find me later. I'll be around to ask me questions if you got them.
Back an hour, a question popped up. And
Okay.
Yeah. Thank you, Joel. Yes. All right. So. So let's introduce our next speaker, this like esteemed gentleman. So João is a network engineer at Fastly, where he's responsible for making dumb switches do clever things. In addition to writing software for network orchestration, João works on protocol design and performance and holds a PhD from University College London or something to that effect. In his younger years, João was a teen star in the Portuguese version of Dawson's Creek. I will leave it to you to guess if it was Dawson or Pacey. Woo!
Thanks, I guess. Thanks. Cool. So Inez has been trying to ask me for a very, very long time to give a talk here. And for a very, very long time, I resisted. Because I'm, like, from the previous events, this is clearly a distributed systems kind of vibe. And I'm none of that. I'm a purely networking person. And so I finally succumbed because Inez is now sitting within stabbing distance of me. And so in doing this talk, I'm going to make a massive assumption, which is that most of you here are not networking people. If you happen to be a networking expert, you're going to be disappointed. But I am going to assume that whatever it is you do, you end up building services or systems on top of the network. And so most of you might have some concept of how the network actually works, right? And you need to because you rely on this intrinsically, right? And so this talk is going to be about how you share a network, right? And if you know anything, you're probably thinking that you know this one, that it's TCP, right? And you'd be wrong, because I literally didn't say that. I said that this talk would be about how you share a network. And TCP is an answer, maybe, probably not. But this talk is actually about the question rather than a potential answer. And so, kind of extrapolating from my assumption, I'm going to assume that for whatever reason, when you tried to look into networking, you were given an answer. And because you were given an answer, you can't fully understand it. And you can't fully understand it because you've actually never gone through the mental exercise of working through the question, right? And so this talk is going to be about 4 papers spanning almost 50 years. And they're all different interpretations of the exact same question. So they're all variations on a theme. And the first 3 are foundational papers in computer networking, which just means no one actually reads them anymore. So the high-level objectives is just to give you, as application developers or system developers, foundational knowledge on, well, how we got here, with what assumptions, and at what cost. And the nice thing about doing like a sequence of papers like this, and the fact that it is actually one of the oldest kind of open problems in distributed systems, is that you get this very, very nice narrative arc, which you kind of see repeated in other systems research and Hollywood movies. And so I'll start at kind of the very beginning. And the very beginning, in my opinion, is a paper written by Paul Barron in 1962 called On Distributed Communications Networks. And the opening phrase is pretty simple. It kind of just asks you as a reader to consider the synthesis of a network which will allow several hundred communication stations to talk to each other after an enemy attack. And so the very beginning of the paper posits that essentially you only have 3 types of topologies, right? You have a centralized topology which has an intrinsic single point of failure. You have a decentralized topology which has much nicer properties and was very similar to the telephone network we had at the time. And there's something inherently new that Barron is proposing, which is a distributed network. And one of the first conclusions is that the decentralized network actually works pretty well if you're assuming randomly distributed failures, right? But inherently, if your threat model assumes an actual enemy attack, then you have to do worst case design, right? And so the first half of the paper is effectively doing a simulation as to what the probability is of a network partition if you attack it. This is great because he does He estimates 288 weapons with a probability of kill. Then he goes on to do something like test the sensitivity of the model to node destruction, then link destruction. Then he does a combination of both link and node destruction. And like, this is literally the most pessimistic paper I have ever read. And it's, of course, it's only paranoia if they're not after you. And this paper was published the month before the Cuban Missile Crisis, right? And so the notion of a threat was very, very real, especially if you consider that actually wiping out a telecommunication network is not that hard because it's just a decentralized model. And of course, we don't actually live in that different an era. We just assess risk intrinsically differently. But the really curious thing is that from Barron's perspective, most of you don't actually work on distributed systems. Because from Barron anchors the definition on the cost of destruction. And so a data center in that regard is just a node, right? Like if you're up against a ballistic missile, it doesn't matter how many containers you spin up. It's like, whatever. And so the first half of the paper asserts that a highly survivable system can be built, even in the thermonuclear era. And this is how you get funding in the 60s, by the way. Like, that phrase is just gold. But from here, the paper, this would have been a nice paper, kind of. But then he does this really wild extrapolation, which is he asserts that if you want a reliable system, then you have to do distributed network, in which case you're going to have a large number of elements. And now all of a sudden it becomes about how cheap can you make this be, right? And so he states, well, you'll need variable data rate links, because in a circuit switch network, you actually have fixed capacity, and all of a sudden expanding that network becomes incredibly expensive, right? Because everything is in lockstep. But you won't only need that, you'll also need variable data rate users. Like, you don't actually know what data is going to come into the network, and you can't assume anything. And that sucks. But if you do these two things, you only need to do it once, and you could have a public utility for data transfer, right? The one thing you need if you want a single network, though, is that you need a magical packet format, which is a standard understood by everything that connects to this network. And he calls this the standardized message block, right? And at this point, you can throw everything you know about resource allocation in networks out the window, right? Because nothing we knew actually applies anymore. Like Poisson, or all that shit completely disappears. And so, how would Barron actually share a network? And his solution is priority marking, right? You have this standard message block, and you give it a mark depending on the priority. And this makes total sense, because if it's supposed to be a military network, and if you work for a defense contractor, then the thing you come up with is that you have different levels of priority which map to separate military function. And then in case of an overload, you just dial down the data rate for the lowest priority traffic, right? It's kind of silly, but you still have this, because this is what the IP type of service field comes from, right? And so this is one way of actually sharing a network. But it's silly. This paper is incredibly hard to read if you don't actually take it in its historical context. But it's actually incredibly important because it really does a wild extrapolation from survivability to a massive global universal data network thing. But it's firmly rooted in old world mentality. But at the end of it, it has a very clear vision of what the internet is, because it's kind of presented as this unavoidable thing due to market economics. But everything in between is left completely open. He has really naive proposals about how to do routing and stuff like that, but none of it actually works. But that's fine, because this is the first phase of any research area, right? Everything is like, wow, this is an exercise to the reader. I'm sure I'll be fine. And this gets us to the next phase, right? And the next phase is the ARPANET. And you can trace back money that funded this straight back to Barron's feasibility assessment from 1964. Now, this is the first diagram in the ARPANET. What no one ever notices is that This is historical because this is the only time that anyone has drawn a network with a single host and a single router. It is the most pointless network of all time, literally. But it's perfectly representative of the next stage of research, right? Which is scientific positivism. Like everything is good. Like if you work on containers, this is where you are. Sorry. This photo is actually Dr. Jonas Salk, the guy who cured polio, right? Which is an amazing feat over nature, right? But in hindsight, it was actually the first victory of post-war medicine. And so it turns out it was just the low-hanging fruit. But if you look at the photo, you'd think the smile would cure cancer or something, right? And so in computer networking, the maximum expression of scientific positivism is 1974's paper by Vint Cerf and Robert Kahn. And it presents TCP. And it makes them be the fathers of the internet in American literature. And so, just saying. And so this is pretty simple. I mean, first phrase, it presents a protocol that supports the sharing of resources that exist in different packet switching networks. And so 12 years after Barron asks the question, this is the standardized message block, right? And this paper does a tremendous amount of important things, right? Like packet fragmentation, transmission failure, sequencing, flow control, error checking, connection setup, all things you take for granted. I'm not going to talk about the things it solves. I'm going to talk about the other stuff, right? Because if you read this paper, if you know TCP and you go back and you read this paper, some of these things are pretty off. It's very unfamiliar, right? The first thing you'll notice if you skim the images is that it has this thing called an inter-network header, and then it has this thing called a process header, but the sequence number is in the inter-network header, and so is the SYN flag. And so that's the first sign that there's something weird about this paper. The second red flag is that Vint Cerf is smoking a pipe. And then it's like, well, if there's an inter-network header and there's a process header, then what the hell is TCP? And helpfully, the paper explains that within a host, we assume the existence of a transmission control program, which handles transmission for other processes. It's a program, not a protocol, right? And so TCP is a user space networking stack around 40 years before you thought it was cool. And then you get to the retransmission phase, and this is my favorite part of the paper by far. So it starts promising enough, which is it states that no transmission can be 100% reliable, and we can all agree on that. And then literally 2 sentences later, it states that the retransmission mechanism will not be called upon very often in practice. Evidence already exists that individual networks can be effectively constructed without this feature. Of course, these sentences are not at odds with each other at all. And so you have to understand that TCP is originally designed. Retransmissions are pathological. They're not the expected behavior at all, right? And so if you have a retransmission mechanism, you need a windowing mechanism just to know how much data has actually been acknowledged or not. And that's fine, but how do you set the window size? Scroll down, and you figure out that a suggested window which the receiver can use to control the flow of data from the sender. This is the main component of process flow control. And so effectively, there's only 2 things that control the window. It's either the sender side buffer or it's the receiver side buffer. And so when Vint Cerf explains that this is about sharing resources, the resource in his mind is the host. The network is never the bottleneck, right? The other interesting thing to understand about this paper is there's no UDP. So UDP actually came after TCP. So they actually only really truly broke TCP and IP out when they figured out they needed something else. And that's interesting because if you think about QUIC, if everyone's heard about QUIC, historically you can frame this as an attempt to reassert what the standard message block of the internet is. Because had we designed UDP before TCP, we would have layered TCP on top of UDP because the reuse is so high. But anyway, how do you share a network according to Vint Cerf and Robert Kahn, right? Well, you just do flow control. And of course, he's a systems engineer, right? Everything came from his perspective from around the processes, like from around the actual application. And so he had a completely top-down view of this from that regard. And historically, this actually makes sense, because if TCP starts as a user space stack, it was overlaid on top of something else. And so the reason he assumed the network was never a problem was because he was building TCP on top of networking technologies like X25. ARPANET was very similar to X25, which provides hop-by-hop reliability, provides flow control, and provides another ton of expensive crap no one needs, right? Was super slow. But that's fine. What could possibly go wrong? There's another amazing thing about this photo, by the way. There's another person in it. And he looks like he missed a paper deadline because he screwed up the time zones. That is phase 3 of every scientific research area. So if you work in consistency, the CAP theorem kind of disappointed lots of people, and this kind of in here. That's fine. In reality, it took a very different form in networking. And if you scroll right to the bottom of 1974 paper, the first person Vint Cerf and Robert Kahn acknowledge is R. Metcalfe, also known as Bob. And Bob was a PhD student in the early 70s, one of the very early contributors to the ARPANET. And Bob and some of his colleagues had an amazing idea. And it's actually an idea that has been making entrepreneurs cash flow positive since the dawn of time. He thought, what if instead of all this, I did nothing? And so Ethernet was born. I don't actually have time to explain how Ethernet works, but there's a small chance that it doesn't. Okay? And so, two things happened in the 80s, right? In 1979, Bob Metcalfe founds Freecom. By 1981, they shipped the first Ethernet adapter. By the end of the 80s, with the explosion of personal computing, Ethernet won the link layer battle. And as a result, Bob Metcalfe becomes a multimillionaire, a venture capitalist, and according to Google image search, a devil worshipper. And the other thing that happens is all these high-speed local area networks start connecting to the internet, which at this point is the digital equivalent of a collection of plastic straws. And so by 1986, the internet stops working, right? And this is where the third paper comes in. And this is kind of the seminal paper of computer networking. Everyone speaks of it with immense reverence, and for a reason. I'm not actually going to make fun of this one. And so Van Jacobson starts, it doesn't even have an abstract, or it doesn't even say introduction, it just starts. And it explains that in October of 86, the internet had the first of what became a series of congestion collapses, right? And fascinated by this sudden factor of 1,000 drop in bandwidth, Van Jacobson and Mike Carroll's embarked on an investigation of why things had gotten so bad. And Van Jacobson is not, or at this time wasn't considered a computer scientist. He was a physicist. And so to understand what was happening, well, take TCP as it was envisioned by Barron and put it on an Ethernet network, for example, right? And this is what a flow would look like. So the y-axis is the packet sequence number, and the x-axis is time. And if a flow were going normally, you'd expect it to always be doing forward progress, right? But that's not what happens because, well, how do you share a network? You do flow control. You send it at whatever rate the receiver is telling you to. And so you send a burst of packets. The network can't actually handle it, and it doesn't provide reliability or flow control for you. And so it drops half of it. And so you time out. And you send essentially almost the same burst over and over again. And so this is an aggravated behavior because you're just multiplying packets without actually getting any of them through, right? And under this observation, Van Jacobson kind of stated that, well, for a system to be stable, for a connection to be stable, it should obey a conservation of packets principle, right? And when he says conservation of packets, it's a concept that comes from physics, right? That for a connection to be in equilibrium, the packet flow is what a physicist would call conservative. A new packet isn't put into the network until an old packet leaves. And this is it's a really kind of intuitive notion, but it's also completely alien to the networking world at this point. And so the amazing thing about this paper is the entire paper fits on one page. The remaining 8 pages are just for regular humans like me and you to understand, right? Like the whole thing is derived entirely from this statement. And he observes that, well, you can decompose this into 3 stages. One is that you need to get to equilibrium first, right? And so you do slow start. And slow start, you just exponentially ramp up until a certain threshold. Now, slow start is not actually slow, but it is way slower than we used to do, which was just send at the advertised window. Once you get to a threshold, you move on to some other phase, and it's congestion avoidance. And effectively here, you are just probing and adapting to changes in equilibrium, right? And so you have a much more conservative ramp up over time in the hopes that more free bandwidth is available. But if you hit a loss, you back out. And if you were to time out entirely, you just go straight back to slow start, right? And the difference is as follows, right? You see that a flow at the beginning, it's actually getting more and more packets per window, but after a while, it just linearly ramps up, and it actually ramps up quite very slowly over time. And it has forward progress at all times, right? Compare this to the at scale thing. So the y-axis is actually the same scale, and that is a pictorial representation of a drunk driver on the right. And so this is worlds apart, right? And so the main contributions of the paper are that, it does give slow start as an approach to equilibrium. It fixes RTT estimation as well, which is quite a hefty part of the paper. Not the most interesting to read, but it's actually pretty nifty tricks he pulls off because they're all out of control theory. And the RTT estimator is important because if you have this notion of a system and you can only inject one packet when the other leaves, then all of a sudden you need to know when the other packet leaves. You need to have a very accurate estimate of that. And not only that, so the previous RTT estimator we were using didn't actually take into account variance. And so under congestion, RTT would vary wildly, and the actual sender was completely unable to keep track of it, right? And then it kind of introduces this notion of congestion avoidance. And so from here, everything is absolutely fine. This paper has messianic properties in the networking world, right? Because it took something that was working remarkably poorly and it made it scale to this day. In effect, if you were to take TCP from back in the day, it would perform remarkably badly today, but that doesn't matter. It wasn't about the solution. It was about this framework that integrated continuous control theory mechanisms. And so you could reason about the model entirely differently, right? Having said that, the best thing about the paper, well, other than the fact that it saved the internet and stuff, is that it is incredibly honest. So actually, no one actually reads the paper. They all just believe it at face value now. This is a paper completely devoid of the hubris of academia. And congestion avoidance, what do you do? Well, if there's no congestion, you increase the window by a linear rate, right? And Van Jacob, this is defined as 1. You increase 1 segment per round trip time. On congestion, if you hit a loss event, or you detect a loss event rather, you do multiplicative decrease, right? And this D is 0.5. So how come? So this paper has amazing quotes. There's a phrase which simply says, there is an analytical reason for this, but it's tedious to derive. This is the only scientific peer-reviewed paper I have ever seen in my life that presents a core part of the paper, and the expression it uses to open a paragraph is without justification. Okay? When explaining the values, he explains that the reason he uses 0.5 as a decrease term, he uses the expression hand waving. I thought this was a term from physics. It's not. And as if that one was any good, his next one is, the 1 packet increase has less justification than the 0.5 decrease. it's almost certainly too large, right? But yeah, how do you share a network? Well, turns out if you ask a physicist, it's just, fluid models. So this was entirely borrowed from hydrodynamics, which of course, everyone here, yeah, sure. But it does instill something else, right? Like if you use this packet conservation principle, you get other properties with it. And one of them that you get is flow rate fairness, right? Because what you're sharing with the packet conservation principle is you're sharing buffer space in the network. And so every flow passing through a buffer that is a bottleneck will get the same proportion of that buffer. And so this means that every flow will have the same rate. This is great. And so for 30 years, the networking community has been incrementally improving TCP, right? So TCP has a bad rep because it's considered kind of a boring research area. And it's super unfair because it's actually seen massive improvements, right? You can think of all sorts of ways. How would you improve RTT estimation? Or how do you infer congestion reliably? Or how do you actually scale to large bandwidth delay product networks and stuff like that, right? How do you do faster window adaptation? So TCP cubic looks nothing like the TCP of Van Jacobson's time. But another area that lots of research went into at some point in time was, well, how do we get the network to enforce flow rate fairness? How do we ensure fairness between flows? And so we get to the final paper, which is from 2007 by Bob Briscoe, which has one of the best opening lines of all time, I think, for a paper, which just says that this paper is deliberately destructive. Great. And it basically, for 8 pages, bashes on flow rate fairness. And so the paper's quite simple. It simply states there are only 3 things wrong with flow rate fairness, but there are only 3 words. So, and so the first thing is, it shares the wrong thing, right? And so what do you share when you share bit rate? And so from Bob Briscoe's perspective, there are only 2 things you can want to share. You're either sharing the benefits or you're sharing the costs. And so if you're sharing the benefits, well, is that it? Not really. Because the benefits, the utility you extract from a bit rate depends on what you're doing, right? And so you can imagine a voice call gets a lot more benefit from the same amount of bit rate than a video call does. And so by definition, if you share the bit rates, you're almost certainly not guaranteed to share the utility function, unless it's the exact same application, right? So that's a bust. Is it sharing the costs? And that's slightly less intuitive. So imagine a link with a flow of data, right? What is the cost of using more data? And, well, the answer is the marginal cost of bandwidth is 0, right? And this is what most capacity planning people, ironically, don't actually understand. So you have the sunk cost of the link, but you can actually amortize that over subscribers over time, right? That's kind of a lease line kind of thing. But bandwidth itself is an ephemeral commodity, right? That's actually the technical term in economics, right? Like, you can't save up bandwidth and use it later. If you don't use it now, it's gone. So the incremental cost, the marginal cost of using more bandwidth is 0. And so imagine you have 2 flows with wildly different bit rates going through the link. The bit rates aren't equal, but the cost is. And so there's no actual necessarily relationship between those 2. I mean, there might be, but correlation, it's not strictly that way. And so if you share the bit rate, you don't necessarily share the costs. And so the paper just asserts that, well, flow rate is a hopelessly incorrect proxy for both benefit and cost, right? If the intent was to equalize benefits, equalizing flow rates doesn't do it. Even if the intent was to equalize costs, equalizing flow rates wouldn't achieve it. And so sharing the bit rate is wrong. But not only that, it shares the wrong thing amongst the wrong entity. And this one's super easy to understand. So if you're sharing bit rates amongst flows, well, I can just create more flows and get a higher percentage of the bandwidth, right? This is just economic free riding, effectively. And the analogy is great. It's the equivalent to claiming food rations are fair because the boxes are all the same size, irrespective of how many boxes each person gets or how often they get it. And so if you share the wrong thing amongst the wrong entities, well, then by definition, fairness is a non sequitur, right? We incorrectly used fairness in the networking community to signify equality. But fairness in real life that's not what it means, right? And so, all my best insults come from this paper, actually. So it defines a fair allocation of rates between flows isn't based on any respected definition of fairness from philosophy or social sciences. It has just gradually become the way things are done in networking. And so the conclusion is obscured by this broken idea, we wouldn't know a good solution from a bad one. And so this paper actually does go into what fair would be in a computer network, right? It doesn't go very deeply into the engineering details, and I wouldn't bother actually reciting them anyway because they're not that interesting. But so what would fair look like? And the basic premise is that all you need is to share the costs. You can't actually understand what the utility function of the application is unless you somehow write the application. But you're never going to be in a position where you write all the applications anyway. So all you need to do is understand what the costs from the networking perspective are. And the cost is congestion, right? So the marginal cost of using a link is 0 until you hit oversubscription. And then all of a sudden it's something else completely. And so the economic term for this is an externality, right? Like if the network becomes congested, each user restricts every other user, which can be interpreted as a cost to all. And so, but this isn't how we do things at all, right? Like if you look at pricing plans and stuff like that, what do you get nowadays? So in the mobile world, you'll normally get a volume cap, right? And so if you have heavy users and light users and insert volume caps, what does it actually do? Well, it reduces the amount of volume you use in per month for a heavy user. But it only marginally improves performance for light users, right? Because you're still bound by the shackles of flow rate fairness anyway. And you just waste a bunch of bandwidth, which is ephemeral, so you can't actually recoup the sunk cost anyway. So that's a mobile world, which is fantastic. But actually, it turns out, like residential markets, it's exactly the same thing. You just do rate limiting instead. And it turns out this is exactly the same, but along a different dimension, right? So heavy users will just probably take a lot longer to download crap, but they will, because that's what they do. And like you still get all the waste of not using the bandwidth anyway. You don't actually have a decent utilization. And so what this paper actually defends is that the correct way of passing on costs is effectively to use congestion volume as a metric, right? I mean, the technical details are kind of hard to get across if you don't understand packet marking. But the idea would be that at the bottleneck, you end up marking packets that actually are above a certain threshold in the queue. And you start accounting for that as the metric of how much that user's packet cost everyone else. And you can think of it in a district, like if you're in queuing systems, right? Like you just have a lock, right? The cost of using a lock is actually how many people are waiting for it, right? And so to a certain extent, if you start passing on that cost, and you start using congestion allowances instead of volume caps or rate limiting, there's pretty sound economic evidence that this would actually maximize social welfare in a network. But the nice thing about congestion volume is it actually has a notion of time, whereas bitrate does not, right? You clamp on bitrate, you can just keep on maxing out that bitrate throughout a month or throughout a day, and the network doesn't account for the differences in those two. And so what the paper actually defends is the notion of a weighted cost, that each application would have a budget of congestion they can cause, but how you use it is completely up to you, right? And so you can have a heavy user that is very cautious and whenever there's congestion stops sending crap. But you could also have light users go way faster than flow rate fairness would imply, right? And go even faster than slow start. It doesn't matter. Like you have a megabyte, just send it all at once. Like as long as you have the congestion allowance to pay for that behavior, it's fine. It's within budget. And the really nice thing is that the notion of fairness ends up being local to each system you actually design it in. So you can have there's an example in the paper, which is a university campus might actually decide that flow rate fairness is the right way to go, but then two universities connecting to an ISP get charged by congestion allowance anyway. And so you can have multiple interpretations of fairness, right? So if you kind of understand that, the Netflix versus Comcast thing that you see in news becomes a lot more interesting because you can actually make sense of it, kind of. And effectively, Netflix causes disproportionate amounts of congestion. Not on purpose, just by the nature of what they do, right? And so Comcast has to deal with this somehow. And obviously they say protect customers, everyone thinks they're joking. Maybe they are, maybe they're not, I don't know. But if you have congestion in an access network, which is supposed to be multiplexed, and that's where all the cost efficiency of using a data network comes from, right? Well, how do you do this? Well, you either rate limit Netflix or block them entirely. If you're in the right country, you can do this. Or you somehow try to demand more money to Netflix, right? And you can demand more money actually by either explicitly negotiating with them, or you can do it indirectly by stalling negotiations or not installing more bandwidth ports when they ask you to and stuff like that. It's great fun. And obviously Netflix will go whine to the FCC that this isn't fair. Except we don't even know what fair is. I mean, by networking terms, everyone uses the word fair and doesn't actually stipulate what the hell they're talking about. And so in the Bob Briscoe model of the world, right, both these companies are wrong. And they're just experiencing an intrinsic market failure. And so the really cool thing is that in the end, like the main assertion of the paper is that it isn't realistic to create the system the size of the internet and define fairness within the system without reference to fairness outside the system. And this is kind of interesting because it kind of posits that the role of engineering, the role of protocol design is not to define the outcome. It's to make multiple outcomes possible, right? Except then you get to security, and I want a different model, so I don't know. Well, how do you share a network, right? Turns out cost, if you ask an economist, ironically, right? And so you'll notice that every person along the way has a completely different way of sharing a network, depending on what their background is. Now, Bob Briscoe actually says that you can use all the previous models, you just have to adjust the market so that you can actually pass on costs to the correct users. And then you actually have, you're maximizing social welfare because you actually incentivize social behavior. Whereas right now you have, well, not right now because no one uses peer-to-peer applications anymore, but whatever. But you have applications which can actually freeload or free ride on network bandwidth. And so if you're an application developer, the only things I actually want you to know about TCP, how many workarounds do you do for broken resource allocation, right? How many distributed systems papers are written on the assumption that TCP is bad with small flows? How many times have you tried to do high performance stuff by batching and reusing connections because of the congestion window? Or opening parallel connections to hog more of it? Or even worse, like artificial limits in multi-tenancy data centers, right? That you can't burst on the network because, well, that's the only way we know how to share is by limiting things artificially. That's great. Don't worry though, it's not just you. Like if you look at HTTP2, the first page, one of the main design choices for restricting HTTP2 to a single TCP connection is that the resulting protocol is more friendly, right? As if friendly is an engineering thing. It's just fantastic. In conclusion, with regards to how you share a network, the great thing is we still have no idea. I mean, we have a very strong theoretical basis, but actually Bob Briscoe's work, although it had a pretty nice practical engineering side to it, the question becomes how do you change a market which is so thoroughly distorted, right? It's very, very hard to change anything the size of the internet. The good news is we know what we have is wrong, and it only took us 50 years. But it's also not broken enough to fix it, right? And And so this is actually the tragedy of truly successful systems, is that you solve every problem along the way with the means you have at your disposal until the only problems you have left are the ones of your own making, right? And so this is the final stage, right? That it's broken, but it mostly works. So this is fine. Thanks.
All right, I have a microphone for questions.
So you mentioned the Comcast Netflix thing as an example of something that is a failure of a protocol, but connections between ISPs aren't determined by protocols. They're done by network engineers, right? I mean, the way that two ISPs connect to each other is, two network engineers get to know each other and love each other very much, and they run a fiber link, right? I mean, that's how ISPs connect. So how does fundamentally the problem between, so I worked at a company that ran a video CDN, and I saw this in a big way, right? I mean, all of these connections between ISPs or between sort of applications and ISPs are determined by policies set by individual people who are having ad hoc handshake agreements and stuff. So how does that that whole ecosystem of people showing up at nanog meetings play into these papers?
If you're a network engineer and you own a link, what do you see? You know nothing about the traffic. You don't know how much congestion is actually going through. You only see utilization, right? And so, if you own a network, you actually have no way of knowing what the costs you are incurring on others is, because TCP/IP is it's just the end-to-end protocol design, right? The actual network is incredibly dumb, and it doesn't actually, it's not even able to understand how many packets of retransmissions on a link at any given time. And so even if you wanted to know, you couldn't, because you're in the middle of the network. And so the only proxies, so one thing I didn't talk about in these papers is that even our assumption of what would be priced was different, right? If you go to Vint Cerf's paper, he explains that packet fragmentation is a problem because pricing is per packet. And that made total sense in the 70s because the processing cost of packets was way higher on routers, right? And so you would pay per packet rather than per byte because the whole cost is in processing the header. And then you get to the 80s and it's just whatever, you kind of start doing 95th percentile. And so the proxy that the networking community literally made up, for kind of inferring what cost is, in the same sense that other people have done other proxies and to reflect it to the user, was 95th percentile. Because it's kind of peak, but not quite. It turns out 95th percentile is incredibly hard to economically model, right? And you can't even understand what the impact is in the long term because you have to do all sorts of weird fiddling to figure out what the impact of this flow today is going to have on your 95th percentile by the end of the month. It's super hard, and it's not even... you can't even cumulatively calculate it properly in most cases, right? It's amazing. So really, the entire networking thing, the whole market is distorted, and you keep using proxy metrics. Networking people don't even accept that their networks might have loss, which is kind of funny. It's amazing. But yeah, does that answer your question? With regards to nanog, I mean, it's just... I think it's people getting drunk together. Is it? Yeah.
It sort of does. I mean, better tools are certainly better, but I think...
No, it's not better tools. It's not a matter of better tools.
Or better visibility is better.
The internet is meant to be opaque. That's how it scales.
Right.
Right? You don't have it by design. This wasn't something someone forgot to do. It's you don't have it by design. And
I'm sure better visibility would help, but there are certainly people that aren't... Either they're not acting in good faith, or... the incentives are such that, if I'm Comcast, for example, Comcast, realistically, is not using up all of their residential bandwidth, right? And
maybe not, but what kind of system do you run?
Well, right now,
do you run at capacity, or do you just buy more when you get to 50%?
Yeah, I mean,
right. So you're just like Comcast, really, right?
But like fundamentally, so basically there are externalities. If I own a fixed asset, right? If I'm Comcast, I have something nobody else has.
Okay, so
I have the incentive to rent seek.
So the difference is that, okay, when an ISP, let's stop using Comcast as an example ISP, which is not. If you actually have to buy more capacity, you have to pass the costs across all users. This is a fundamental reality, that you have subscribers. And so imagine an ISP has 90% of people who just use email. And then you have 10 people who are free riding the entire network. It doesn't matter how much you increase capacity. Like, at some point, the 90% who use it for email are going to say that the cost is absolutely exorbitant, right? And so this is, the cost structure goes down all the way to the residential user. You probably have a skewed perception of, oh, all this capacity is for free or whatever, but that's because you're a power user by definition, because otherwise you wouldn't be here, right? But for most residential people, it's insane that you even pay like $50 for connectivity in a first world country.
Go.
Yeah.
Hi. I was going to say for the for cost allocation and kind of you're just going to solve an optimization problem, assign costs. Isn't part of the problem that you're actually going to want to have a dynamic coupling across an application? So you're actually going to want to buy essentially costs over time that are going to be linked on an application basis, and you therefore need kind of like a forward options market on congestion in order for me to actually solve kind of a problem for allocation over the lifetime of a flow or the lifetime of what an application will want.
Yes, well, so this is part of the problem with the actual deployment model, is because people can't actually figure that out. And so 95th percentile, I kind of bash it, but it's very intuitive. The congestion, you'd have to get some familiarity as to what the application profile is. But the question was forward options.
Well, like with that, are there ways to do that? Because I have a power systems background, and there you have locational marginal prices, but you still need to forward forecast them, and a lot of that is that it's a contingent problem that everybody needs to solve, and it's dynamically coupled, and that most of the things are that the price now is going to be contingent on that. And has it been good enough for networks to do some deployment on this? Because power is even worse than this, so never go into power.
That is hilarious, because power systems is used as a shining example of this. So the interesting thing about the power systems is that one of the main complaints of this system, the idea that you pay for what you get, which is what you get for what you pay, is incredible in networking. But one of the main complaints is that then you have a variable cost to the user. But in networking, it's slightly different because you can do a token bucketed approach where you have an allowance. And so what happens is if you exceed your congestion allowance, all you start to suffer is preferential dropping. Like all your traffic just is the first to die. And in power systems, you can't do that, I believe. Yeah.
Buffers are expensive because you can't build a grid-scale battery. So like DRAM is really cheap, very expensive for power systems.
Yeah, okay. Yeah.
So I have a question with respect to how you pack the capacity of the network. Is there a way in which you could consider, it seems to me congestion is effectively a transition between laminar flow and turbulent flow in a network, and therefore you could consider, what's the knapsack, kind of do a knapsack problem, like how big are the boxes that you're trying to stuff down your pipe and how do they fit into that pipe, and maybe have an adaptive packet sizing to try and ensure that the capacity utilization that you're getting is a function of the size of the packets that you try to stuff.
First off, you have vastly overestimated how technical I am. And secondly, this is byte. So congestion volume is measured in bytes, not packets. So the adaptive element of packets.
A packet is a sort of a byte size, I would think of it as
it depends how you reason about in units. But anyway, we only have one MTU anyway. But yes. Yeah. But there is effectively what you are talking about in terms of adaptive packet size. In this case, is factored into the congestion controller you use at the edge, because that is a minute scale. You have to reason about how you perform over the entire flow. So effectively, you'd have a lower than best effort congestion controller, and that ends up doing the same effect stretched over time, I believe. Adapting it by packet size.
So what I'm thinking is that, for example, as you're in the sort of model discussed, you've got a certain capacity, and you have to look at stuffing a packet in the front, and basically that's replacing.
When you say you have a certain capacity, do you assume that that's fixed?
Well, I'm assuming that at some point in the network your pipe is so thick, and so there's only so much you can stuff down it. Yeah,
yep.
and I guess talking with respect to what the previous questioner asked, or in fact the one before, about you having a lot of capacity at home. I mean, it's not taking into account that you have congestion points where the network converges and you're pushing. Yep. And so this is really the issue that Comcast has. In that it's often sending the same data to different users down the same path.
It might be Comcast doesn't have this.
Oh, sorry. I mean, I know ISP. Sorry.
Yeah,
ISP. An ISP. So it could be Verizon or.
Yeah.
So as you're pushing these packets down to your endpoints, and they happen to converge through particular nodes on the tree on your leaf, and you've not got a truly distributed network. You've got this sort of multi-point failure position. Sorry, I'm
we can talk about this. Somewhere else. But I think there's an interesting I think you're reasoning about capacity, and you have to reason more about the buffers. And we can talk about this. Any
questions?
No.
So I'm curious. Let's say you have two parties that are trying to solve this market failure problem. What are some practical ways that they could do this if they were on a local network, or they didn't have to worry about third parties free riding on it?
So two parties, if you're within a data center, you can realistically actually do this. So if you read Bob Briscoe's work, it assumes congestion marking on the switches or routers. And it uses ECN, which is actually implemented by every router ever for the last 10 years at least. So you can actually turn this on realistically in a data center. You'd have to implement all the user, like the host side functionality, and then figure out if it would actually work. Actually, data centers are a good environment for this because it's effectively all under the same ownership. You have multi-tenancy by nature, but you also have very little idea of what the costs are in terms of networking. There's also this other thing, which is that for the most part, most people don't assume they're network constrained, right? Most people are just like, oh, it's the database is the problem, or just storage. It's always the database, though, let's be honest. You only really get network constrained once the network engineer screws it up, right? And all of a sudden, you have 2 less links and nothing works because it turns out you didn't actually provision any sort of failback as to what is critical traffic versus what is just backup crap running in the background, right? So if you're interested in knowing more, I can tell you, I can point you at more papers. But from the Bob Briscoe paper, you can easily find something called re-ECN, and that's a fully blown kind of specification for a protocol, and it only uses commodity. Like you can use it with just commodity switches. Most of the actual logic is on the user side, and it also, if you just do it within a single data center, lots of the really thorny problems around this actually disappear, which is how do you incrementally deploy this across different networks, and the fact that no ISP in the world does congestion packet marking. So, okay.
Hey, oh, geez, that's loud.
Yeah.
So maybe you answered this and it just went right over my head. Is there any issue here about differences in demands for latency versus throughput on these links? And does that play into this economic model in any way?
It actually does, because you can start reasoning not only about the amount of traffic you have, you could just send every packet duplicated, and you just cause more congestion, but you'd pay for it because you don't have that much traffic. And so the trade-off between latency versus the amount of traffic throughput is completely left up to the applications in this model, right? You can actually start specifying different strategies effectively. And this is the thing that TCP as a resource allocation mechanism is absolutely terrible at. That it doesn't give you a choice, and so you end up doing weird stuff around it to work around the limitations. And it's kind of easy if you just have a single application within the data center and everyone has the same patterns. But once you start mixing traffic patterns and classes, it gets super hard to reason about. And so the only thing is that like congestion volume becomes a currency. Think about it that way. And so what you spend it on is up to you.
All right, I think we have time for one more question. Okay, you want?
Oh, sorry. I know nothing about networking, so I guess this is kind of related to like the physics-related sort of like analogy that was mentioned in I guess like the second or the third paper. So like a lot of sort of like these notions of like rates versus volumes, so on and so forth, like don't really seem to rely on like the history of the inputs into the system. And to an extent, I guess you could say that they're memoryless.
Yes.
So, but you know that, say, for someone like Netflix, that there, say, could be like a periodic input of traffic. That like every day at 8 p.m., you know that there's going to be a big spike of people watching TV. And so, like, do notions of like, you know, prior history for people on that network sort of have any sort of like additional implications when you assume that like that it's not really memoryless, because like, you know, someone who's consuming the bandwidth probably will do so in a predictable way?
I'm sure lots of people have spent years of research on that, but it kind of violates the first paper, which is that if you assume nothing, you can encompass everything. And so the whole point of like, if you're starting to build memory into the system, you become progressively more and more like the phone network kind of thing, which is you become designed to cater for a specific use case. And so that's why generally people don't do it. That, and it's hard. But the first reason is much more eloquent.
All right, let's give it up for João. Woo.